So we've seen the Maclaurin series before. So we've seen this Maclaurin series before. If you want to map a polynomial on top of, let's say, this function cos of x, you would simply follow this series. So f of 0, you would put 0 into here. So remember, with the Maclaurin series, you always evaluate it at x equals 0. So at 0, you put this into here. So cos of 1 would be 1. So this block here will then give you this block here, and then for the next term you would look at f prime. So f prime would be minus sine of x evaluated at 0. So put 0 into here. Sine of 0 would be 0. So this whole thing here would be 0. So it disappears. And then for the next one, for the next term, we would look at the second derivative. Well, the second derivative would be minus cos of x. Well, evaluated at 0, you would put 0 into here. So cos of 0 would be 1. So that would be negative 1. So this would then give you your negative 1 here, and then you've got your x squared, and then you've got 2 factorial. So this term would generate this number 1, and then this one here will then generate this next term here. And then if you look at f triple prime and so on, this thing here would then be 0, and then the next term would then give you this one here. So if you get a graph plotter and plot this, it will generate this blue line here. You see here you've got x to the power 1, x to the power 2, x to the power 3, and so on. If you take it all the way to infinity, then the blue line will map on top of the red line, on top of the cos graph. So that's the Maclaurin series. We've seen that in the past. So this here is just revision. Now I'm going to introduce you to the Taylor series. So with the Taylor series, well, with the Maclaurin series, you always evaluate it at x equals 0. With the Taylor series, you evaluate it at some point other than 0. Let's say at a. So you would evaluate it at a. So with the Taylor series, everything's pretty much the same, but then instead of everything's pretty much the same, but with the Maclaurin series, you always evaluate it at x equals 0. With the Taylor series, you evaluate it at any point. It could be at a here. So this is your Maclaurin series. This here is your Taylor series. So it's pretty much the same. Here with the Maclaurin series, you would look at f of x evaluated at 0. With the Taylor series, you would with the Taylor series, you would look at f of a, which would be this point here, and then you would look at the derivative, the first derivative, but rather than evaluating at 0, you would evaluate it at a. So with the second derivative, rather than looking at the second derivative at 0, you would look at the second derivative at a. So going back to here, so this is your Maclaurin series. This is your Taylor series. So rather than looking at f evaluated at 0, you would look at f evaluated at a. Rather than looking at the first derivative at 0 evaluated at 0, you would look at the first derivative evaluated at a. And then rather than x, you would look at x minus a. And then the second derivative, rather than looking at the derivative at 0, you would look at the second derivative but evaluated at a. And then you've got your 2 factorial and 2 factorial. And then rather than looking at the third derivative at 0, you would look at the third derivative at a, and so on, all the way to infinity. Okay, so pretty much the same, but rather than evaluating at 0, you would look at it at a. So let me give you an example. So let's try and hang on. Let me give you an example. So we're going to do exactly the same thing, but rather than centered at x equals 0, we are going to center it at, let's say, a, somewhere here or whatever, anywhere at a. Okay, so let me give you an example. So this is your formula for the Taylor series. So we need, so this is our function here. Let's find the first derivative. Let's find the second derivative, third, fourth. So looking at this, we would need to look at the original function evaluated at a. So put a into here. So this would then give us cos of A for our first term. It would then give us cos of A for our first term. Now for our second term, we would look at the first derivative, but evaluate it at A. So that would be sine minus sine of A. So that would be minus sine of A. But rather than having it at x, with the Maclaurin series, it's just x. But with Taylor series, it would be x minus A. So it would be x minus A. And then for the third term here, we would need to look at the second derivative. So look at the second derivative, evaluate it at A. So evaluate it at A. So that would be minus cos of A over 2, remember. So that would be minus cos of A over 2, and then you've got this thing squared. And then for the third term, you would look at the third derivative, evaluate it at A. So that would be positive sine of A. So that would be positive sine of A, 3 factorial, and then this thing to the power of 3, and so on. So you can take it to the fourth one. So the fourth one will then give you this. Something to remember, at this stage, you don't really understand why the Taylor series work. I'm asking you just to accept it for the time being. So using the Taylor series for cos of x, it will then generate this. Now, if you get a graph plotter and plot this, so you would have to add A as your slider. So depending on your graph plotter, most calculators will allow, when you press cos of A, it will then ask you to add a slider for A, because it will then ask you to add your slider for the A. So it depends on your graph plotter. Well, get a graph plotter and plot this. It will then generate this. So by you adding a slider, you can actually slide. So we are evaluating at A. You can actually slide A back and forth, and then it will draw the graph accordingly. Well, if you get a good graph plotter, let's say, so I've got a graph plotter here. Okay, so if you slide it back and forth, it will generate it will draw the best fit for cos of x. So you can slide it back and forth here. I hope you can see this. So with the Maclaurin series, you always evaluate it at 0, which will be this thing here. It will generate this. But with this Taylor series, it doesn't matter where you evaluate it. At A equals here or here or here, anywhere. Now you can slide it back and forth. Okay. Well, play around. Get a graph plotter and just play around. Okay. So your Taylor series will generate this. Remember, the graph plotter just shown you. I've only taken it up to the power of 4. You can take it even further. The further you take it, the more accurate it will become. Okay.